This is going to be over section 23.10. We're going to be looking at polarization. So the direction of polarization of a linearly polarized electromagnetic wave is the direction of the electric field. So a polarizing filter passes radiation that is linearly polarized along its polarizing axis and blocks radiation polarized perpendicular to that axis. So Mollusc's law states that when polarized light of intensity I max is incident on an analyzer and phi is the angle between the polarizing axes of the polarizer and the analyzer, transmitted intensity is going to be reflected as this. Brewster's law states that when unpolarized light strikes an interface between two materials, the reflected light is completely polarized perpendicular to the plane of incidence if the angle of incidence is given by this. So you can see here, you can see some polarization here, and then if you put the two parts of the sunglasses together, you see absolutely nothing getting through. So it's filtering out that light depending on the angle at which it's coming through. All right. So we've got a string from chapter 12 whose equilibrium position is along the x-axis, displacements along the y-axis. In this case, the string always vibrates in the xy plane, but the displacements might instead be along the z-axis. In other words, that you can oscillate however you want it to on these axes. The direction along which the displacements occur is going to be called the polarization direction of the wave. So the concept of polarization actually applies to all transverse waves, including electromagnetic waves. So here we've got a transverse wave going up and down. It is perpendicular to the motion of the wave, and it's linearly polarized in the y direction. So the concept of wave polarization applied to transverse waves on a string. That's what we're looking at here. Transverse waves linearly polarized in the z direction. The concept of wave polarization applied to transverse waves, again, in a string. So you've got a slit here through which this goes. So you've got this slit, which is going to function as a polarizing filter, passing only motion in the y direction. So in other words, you've got oscillations going on this way and that away, because you got light that's unfiltered and it's coming through. What this particular barrier is attempting to do is to just get that light that is fluctuating up and down in the y direction. So when it only has y displacements, we say it's linearly polarized in the y direction. If it's in the z direction, it's linearly polarized in the z direction. So for mechanical waves, we can build a polarizing filter that permits only waves with a certain polarization to pass through. And that's what you just saw. So the string can slide vertically in the slot without friction, but no horizontal motion is possible. This can also be applied to electromagnetic waves, which also have polarization. Electromagnetic wave is a transverse wave. The oscillating electric-magnetic fields are perpendicular to the direction of propagation and to each other. We define the direction of polarization of an electromagnetic wave to be the direction of the electric field vector and not the magnetic field vector, because most common electromagnetic wave detectors, including the human eye, respond to electric forces on electrons in materials and not the magnetic forces. If we did, we would look at it in a different perspective. So polarizing filters can be made for electromagnetic waves. The details of the construction depends on the wavelength. So for microwaves with a wavelength of a few centimeters, a grid of closely spaced parallel conducting wires that are insulated from each other passes waves whose electric fields are perpendicular to the wires. So in other words, we've got incident polarizing light. We've got filters right here, and they almost completely absorb horizontally polarized components of the light. So the transmitted light is linearly polarized in the vertical direction. In other words, any oscillation that's going through here on this side and going through on the axis, we're fine, or those get eliminated. The stuff that goes up and down as we go through is the stuff that gets transmitted. So the most common polarizing filter for light is a material known by the trade name Polaroid, widely used for sunglasses, and polarizing filters for camera lenses. Material developed by Edwin H. Land incorporates substances that exhibit dichroism, a selective absorption of one of the polarized components much more strongly than the other. So a Polaroid filter transmits about 80% more or more of the intensity of waves polarized parallel to a certain axis, called the polarizing axis, but only 1% of the waves polarized perpendicular. So it doesn't completely get rid of it, but it massively reduces it. So light from ordinary sources doesn't have a definite polarization. The antennas that radiate light waves are the molecules that make up the sources. The waves emitted by any one molecule may be linearly polarized, like that from a radio antenna. But any actual light source contains a tremendous number of molecules with random orientations. So the light emitted is a random mixture of waves that are linearly polarized in all possible transverse directions. An ideal polarizing filter or polarizer passes 100% of the incident light polarized in the direction of the filter's polarizing axis. So you've got light coming through here. You've got a polarizing axis. In other words, I want only light that is at that particular angle, or that oscillates its electric field in that particular angle. If that's what you want, you put that in there, and this is the only stuff that gets let through. So the intensity of the transmitted light is the same for all orientations of the polarizing filter. For an ideal polarizing filter, the transmit intensity is half of the incident intensity. So that's what this polarizer actually does. Okay, so we can resolve this into a component parallel to the polarizing axis and a component perpendicular to it, because the light is a random mixture of all states. These two components are on average equal. So the ideal polarizer transmits only the component parallel, so half the incident intensity is transmitted. Now, let's say we put a second polarizer in between the first and the photocell. Polarizing axis of the second polarizer is vertical, and the axis of the first polarizer makes some sort of angle. In other words, phi is the angle between the polarizing axes of the two polarizers. We can resolve the linearly polarized light transmitted by the first into two components. In other words, we're going to make it a vector. The electric field that's coming through is like this, but we've got a component that is parallel to the up and down axis, and then we've got a component here that's perpendicular to that. The linearly polarized light from the first polarizer can be resolved in such a way, and that way, when it comes to the analyzer here, the intensity I of the light from the analyzer is maximal when this angle here is 0. At all other angles, this is what we come up with. So we can see that same kind of thing going on here with sunglasses, with polarizing and having it be perpendicular. And so this is Mollusc's law. Again, this intensity is going to be watts per meter squared. If the incident light is unpolarized, then this is what we come up with. If theta is equal to 90 degrees, then no light is transmitted through the filter. So polarization by reflection. Unpolarized light can be partially polarized by reflection. So when unpolarized light strikes a reflecting surface, between two optical materials. Preferential reflection occurs for those waves in which the electric field vector is parallel to the reflecting surface. So here the plane containing the incident and reflected rays and the normal to the surface is called the plane of incidence. At one particular angle of incidence called the polarizing light or the polarizing angle, only the light for which the electric field vector is perpendicular to the plane of incidence is reflected. The reflected light is therefore linearly polarized perpendicular to the plane of incidence, as shown in this figure. So we've got unpolarized light. We've got it coming through at a particular angle here. If light is incident at a different angle, then the reflected light is partially polarized. So the reflected light is weak and 100% polarized off of this reflecting surface. And it's 100% polarized parallel to the reflecting surface. The refracted transmitted light is strong and slightly polarized in the plane of incidence. So when it's incident at the polarizing angle, none of the electric field components parallel to the plane of incidence is reflected. This component is transmitted 100% in the refracted beam. So the reflected light is completely polarized. The refracted light is a mixture of the component parallel to the plane of incidence, all of which is refracted, and the remainder of the perpendicular component is therefore partially polarized. This is the reflected light is completely polarized. This is partially polarized. Brewster noted that when the angle of incidence is equal to the polarizing angle, the reflected ray and the refracted ray are perpendicular to each other. In other words, right angle. In this case, the angle of reflection is equal to 90 minus this. So we come up with this relationship from the law of refraction, Snell's law. Come up with replacing a few factors here. We can come up with this relationship, the polarizing angle, the tangent of that, and how the refractive indices end up playing out. So we've got a component perpendicular to the plane of the page, comes in. The reflected and refracted rays are perpendicular to each other. And this is known as Brewster's law. It states that when the tangent of the angle of incidence equals the ratio of the two indices, the reflected light is completely polarized.